Greetings, fellow learners. In this video, we are going to take a look at YOLO. You only look once. The what, the why, and the how. So let's get to it. So let's start our discussion off with object detection. It involves the localization and classification of objects. Localization, where is an object of interest? Classification, what is that object exactly? And YOLO is an end-to-end trainable neural network that does exactly this. And, for YOLO, we essentially create all bounding box predictions and all of these classifications in a single forward pass. And hence, it looks only once. So that's YOLO. So why do we have YOLO right now? Well, in 2013, kind of the state of the art for object detection was these class of RCNN family networks. So RCNN essentially had 3 stages to object detection, where we'd first generate region proposals. For each region proposal, we would try to convert it into a vector of features using a convolution network. And then we would try to perform a classification. We would train a bunch of binary classifiers and then try to determine if each of these proposals is that specific object or not. And we would end up with localizations and classifications. Now, like this, over the years, there was many additions to this in order to decrease this inference time. So the initial architecture that I just proposed was about 50 seconds just to get a single inference. And the performance was 58% on the Pascal object detection dataset from 2007. Now, with fast RCNN, essentially the last 2 stages of detecting features and as well as that SVM classification were kind of merged into this neural network approach using ROI pooling. And this brought down the inference time just to 2.3 seconds for a single image while increasing performance. We have a full video on this if you want to check it out. And then we had faster RCNN, which actually made an end-to-end neural network approach by even reducing this generating region proposal phase. So this entire thing essentially became an end-to-end trainable neural network, and it was devised around the same time that YOLO, the first version, was also devised. And it cut down inference time to 200 milliseconds while increasing performance as well. YOLO, on the other hand, while despite, it might have had lower performance on object detection overall, it still had 10x faster inference time for a single image than the faster RCNN. And this made it very suitable for real-time applications. So this is kind of the big reasons of why we have YOLO. Now, apart from this too, there's actually a few other reasons as well. First, YOLO is real time, then it's simple, it leverages global context, and it learns generalized representation of objects. So we can go through each one of these just to add some color. So real time, we just hit on this topic. Now, YOLO is simple. So essentially, a single forward pass of a single convolution network can help us get the bounding boxes and also these classifications for all objects in an image. Super simple architecture. And this is opposed to the very complex architectures of the RCNN family. Again, if you want some more information on this, we have videos on each of those 3 RCNN models. Next, YOLO leverages global context. So essentially what this means that it sees an entire image when making localization and classification decisions. And this is different from fast and faster RCNNs, which only look at regions instead of the entire image when making decisions. So for example, this part of the image here kind of looks like a logo. But if you actually zoom out and look at the entire image itself, you'll realize that it is actually a stop sign. And hence it is classified more correctly. And another aspect of this global context also has this nice little advantage that it gives YOLO in that it learns generalized representations of objects. So what this means is that, YOLO relies on shapes instead of extracting exact texture features. And this helps identify different styles. And this is once again because it looks at the entire image when making decisions, and so it isn't really distracted by local texture variations. And as an example of like what I mean by this is that, if we have this input image in this style, let's say that YOLO was trained on actual, people images or cat images and dog images. Now, even though it's never seen this kind of like painting before, it is still able to correctly identify this as a person and this over here as a cat. So it works as well out of the box, and hence it learns generalized representations of objects. So that's about the what and the why of YOLO, and I hope all of this makes sense. Now let's look at the structure of YOLO. Now this here is just an image from the paper, but I thought that it would be easier to kind of blow this up and actually look at the transformations that happen throughout. So let's take a look at that. So over here is like a draw.io representation of exactly that YOLO architecture. So the input image is going to be 48 x 48 x 3 for RGB, and input images are resized to be of this shape. We then perform a 7 x 7 convolution with a stride 2 and a padding of 3. And then what this entails essentially is that it's going to create a 224 x 224 feature map, but we have 64 such filters, and hence it's 224 x 224 x 64 channels. Next, we perform max pooling with a stride 2, 2 x 2 of stride 2. This is going to lead to a tensor of 112 x 112 x 64. And you can imagine here, in between we're going to have like some activations. I didn't add them in here because it doesn't really change the shape of these tensors, but it does add some nonlinearity and more richness to the features of this original image. So we then perform like 3 x 3 convolutions with a stride 1 and padding 1, and using 192 such filters, we'll get 112 x 112 x a 192 feature map. Then perform max pooling in the same way to decrease the width and the height of this tensor by 2-fold. And then we perform a pointwise convolution, and now this is going to essentially adjust the depth or the number of channels in our tensor. So from 192, we made it 128. And then we have 3 x 3 convolutions, pointwise convolutions, and we just keep performing these transformations. Now, over here, I just put like 4x over here just to show that this pointwise convolution followed by a 3 x 3 convolution is done like multiple times over. And then until eventually we're going to end up with, after this 3 x 3 convolution, we're going to end up with a 7 x 7 x 1024 dimensional tensor. And this tensor is going to essentially have a rich feature representation of the input image. So what we do is now we flatten this out. If you flatten this out, it's going to be like 50,176 dimensions. We'll pass it into a couple of feed-forward layers, and ending with this feed-forward layer of 1,470 dimensions. And then we're going to reshape this into a 7 x 7 x 30 dimensional tensor. Now, this represents some information about the image, and specifically, it's going to have 98 bounding boxes, as well as some confidences in those bounding boxes, plus classification information. So, I hope that this architecture is better spelled out than like the image that you see in the main paper, and I'll share this too in the description below. So now we have the structure of YOLO. But why exactly does YOLO map this 448 x 448 x 3 image to a 7 x 7 x 30 tensor? Well, let's take a look at that. So consider this image, and what we're going to do is we're going to grid this image into 7 x 7 grids. And each grid cell is essentially going to be mapped to a class probability, assuming that an object exists. So let's say here, for this case, YOLO is trained to recognize 20 object classes. And for each of these cases, let's say in this grid cell, assuming an object exists, we can try to map it to some class probability. So there is like a 4% chance that this grid cell will contain like a dog, given that, an object exists in this, as a part of this grid cell. Similarly, there's going to be a 27% chance that given this, there is like some object in this grid cell, it's going to be a chair, and so on. So you can see that each of these 49 grid cells will be associated with 20 numbers, and this 20 numbers is the number of object categories. So that's one aspect. Right, now each grid cell will also make 2 bounding box predictions. It is responsible for 2 predictions. And the idea here is that, well, each box is going to be represented by 5 numbers. So the first, to represent this bounding box over here, right? So it can be represented by 4 numbers itself, which is the X and Y coordinates. This is like the top left corner pixel of the image. And then W is the width of the image, H is the height of the image. And then we have also a confidence of exactly like how confident we are that this here contains an object of interest. And that's like 67%, for example. And similarly, for this other bounding box, we have this here, right? So this means that each grid cell is also associated with 10 numbers, that is 2 bounding boxes. And so each grid cell is thus associated with 30 numbers, that is 20 indicating class probabilities, assuming the object is present in the grid cell, plus 10 that indicates 2 bounding boxes and the confidence that there is an object in those bounding boxes. So I hope that the interpretation of each number in this 7 x 7 x 30 tensor makes more sense. If certain aspects of this didn't make sense or are not quite clear, I think it'll be more clear as we walk through the training of YOLO. So to train YOLO, let's say that we take a training sample image. Now we're going to bin this into 7 x 7 grids, and we're going to use the ground truth bounding boxes. So this is like the ground truth for the dog and the ground truth for the chair right here. And what we do is now we're going to determine the grid cell that contains the centers of these bounding boxes. Right here, this is the center, this is the center here, it's contained by this grid cell, this is the center here, and it's contained by this grid cell. And essentially, these grid cells now are responsible for predicting the bounding box. So we assign this grid cell is responsible for predicting this dog, this grid cell is responsible for predicting this chair. So now let's make a forward pass through YOLO to get the tensor, and then we compare it to the labels to get a loss. This is what it looks like at a high level, but I'm going to be zooming in a little bit here. So we have this image over here. We pass it into YOLO, and we're going to essentially get a 7 x 7 x 30 dimensional tensor. And just to summarize what this actually means, if we blow up this tensor, it kind of looks like this, where we have like cell 00, cell 01, cell 66, all of the 49 cells. Each of these 49 cells will have like a class probability distribution of, assuming that there is an object associated with this grid cell, what is the probability that it is of each of these classes? And so we have 20 numbers for each cell. Similarly, we also have for each grid cell 10 numbers, which indicate the 2 bounding boxes, right? So it's 10 numbers for 2 bounding box predictions per grid cell. So that's how we get the 7 x 7 x 30 dimensional tensor. And now if we wanted to actually map these numbers to what they really mean, these class probabilities essentially is going to assume, let's say for this, image, it's basically saying that, hey, this grid cell, if it has an object, it's probably going to contain a dog. Or this grid cell, assuming that there is an object, it's likely to contain a chair. Similarly, these numbers over here is going to give the 2 bounding box predictions. So it's going to be like this, the orange ones over here, the 2 orange boxes here are going to be associated with this grid cell. And for this grid cell, it's associated with these bounding boxes over here. So, and also the confidence values are given by the thickness of these boxes. So the larger the box, that means it's more confident in the prediction that there's an object there. And so we can kind of combine both of these together, and the overall prediction basically means okay, so for these 2 bounding boxes, we're essentially predicting that there is a dog. And for these 2 bounding boxes, the little blue ones over here, we're essentially predicting that there is a chair. So that's our prediction. And because this is a training sample, we have a label too. And when we have a label and we have a prediction, what we can do is determine a loss with a loss function. And so this is our bigger view over here. And once we have this loss over here, what we can do is backpropagation. So essentially this loss is backpropagated through YOLO. And all the weight parameters here are updated and the network learns. So of course, this is like kind of a high level of what's going on, but now let's actually get some more intuition on what this loss function actually entails. So this here is some scary little math that you see over here, but in reality, it's actually like quite a simple squared error loss function. And in order to explain this, I'm actually going to explain it with like some images over here. So hopefully, this math is not going to be too scary. And if you want to dive deep into it, you can on your own time. So let's say in our label and prediction over here, we wanted to determine the grid cell that's responsible for this bounding box over here, right? And, this is the grid cell specifically because this is the one where the center of this bounding box over here, we determined that it lies in this grid cell. And so this grid cell is responsible for making this prediction. But this grid cell also makes two of these bounding boxes over here, one and then two over here. So this is responsible for detecting the dog. It predicts B is equal to 2 bounding boxes. And the one with the largest intersection over union with the label bounding box is responsible for detecting the dog. So in this case, there's like 2 bounding boxes, but this bounding box over here, this big one over here, has probably a larger overlap with this label, and hence it is responsible for detecting this dog. Now, that difference, the difference between this box over here, the label, and this box, the prediction, is going to be given by, these values. We have an X, Y, each of these is like represented by an X, a Y, a W, and an H. So that's like the label is X, Y, W, and H. And this bounding box is the same thing, but with the hat, X hat, Y hat, W hat, H hat. And so just taking the regress differences, you get like, this is what that represents here. And we do this for every single grid cell and for every single bounding box. Next, we also want the confidence for the responsible bounding box to be the IOU, the intersection over union, with the ground truth. So because this contains an object over here, the IOU, the overlap of these two, which is represented by like the IOU, that should be represented as the confidence of this bounding box. We also want to suppress the predicted bounding box that is not responsible for an object. So the ground truth confidence should be 0. So that's for this one over here. It doesn't represent an object. We want to like kind of push that during the training to be 0. And that's done using this part of the loss function. Next, for each grid cell that is responsible for an object, we want to ensure the class probabilities represent the correct object of interest, right? And in order to do that, we have this over here. This classification loss is represented over here. Now, in order to make sure that this is like for the localization part of the loss, and this is for the classification part of the loss, we want to make sure that localization and classification can be weighted, appropriately. And so in this case, like it would kind of be weighted the same, but the problem is as the number of classes increases, we could see that classification loss could arbitrarily just become larger. We don't want that to happen. And so we would like kind of inflate this value over here using a hyperparameter. And this, for this specific case, with 7 x 7 grid cells, 2 bounding boxes per grid cell making a prediction, we'll set it to 5. And most grid cell bounding boxes are also like not responsible for objects, right? We would have like 98 predictions coming from YOLO, but in this case, there's only like 2 bounding boxes that actually exist. And so training can be destabilized by all of those bounding boxes that are really not predicting any object. And hence, we kind of want to regulate those. And this is done by adding this hyperparameter over here, this lambda no object. And in this case, we set it to 0.5. And next, you see that here we were taking just like the difference of, it's like the difference and squaring them. But in this case, we see these like square roots over here. And this is to ensure that we're not like over penalizing the small differences from large bounding boxes more than small differences from small bounding boxes, which may be the case. And so this is why we add like square root terms to mitigate those differences. So we don't want to penalize large bounding boxes. And so that was kind of the entire training. So I hope that all of that made sense. And now inference is actually quite simple and straightforward. let's say that you take this image of a cute little corgi over here, you run it through YOLO, then you're going to get a tensor of 7 cross 7 cross 30. This represents essentially 98 bounding boxes with classifications and confidence that you see over here. So each bounding box is associated with a classification and a confidence. And then you can perform like NMS. So this is non-maximum suppression. So that's basically sorting these bounding boxes in descending order of like confidence and then removing very highly overlapping bounding boxes in order to get this final image with a localization and a classification. And I hope all of this now made sense for YOLO. Quiz time. Have you been paying attention? Let's quiz you to find out. Why would we use YOLO over RCNNs? A. YOLO can be used in real-time systems. B. YOLO has better performance. C. The forward pass for YOLO during the inference is quick. Or D. YOLO better leverages global context. Note that multiple options may be correct, and I will give you a few seconds to answer this question. The correct options are A, C, and D. Did you get them right? Please comment your reasonings down in the comments below and let's have a discussion. And at this point, if you think I deserve it, please do consider giving this video a like because it will help me out a lot. And that's going to do it for quiz time, but before we go, let's generate a summary. So in this video, we took a look at what YOLO is. It essentially is a method of object detection that has an end-to-end trainable neural network where all of these localizations and classifications are produced in one forward pass simultaneously, and hence it looks only once. We also took a look at some advantages of like why we would use YOLO over, for example, RCNN. One is that it's real time. It's simple, it leverages global context, and it learns generalized representations of objects. We then took a look at the neural architecture of YOLO with like a draw.io diagram and also understood what this like 7 cross 7 cross 30 tensor represents. And essentially it's a 7 cross 7 grid cells where 20 numbers represent class probabilities, assuming like an object is present in the grid cell, and 10 numbers indicate 2 bounding boxes predictions along with their confidences. And then we took a look at the training procedure here where we have an image, we produce this 7 cross 730 tensor that, it blows up to look like this. This essentially is the bounding box predictions and also their classifications for the bounding box. And given the label, we can also compute a loss using the loss function. And this loss function is like a squared, like a regression loss function that kind of looks like this, where we, at least at a high level, explain what each of these terms represent. And I would encourage you to kind of go through the paper and also work out the math just to understand better how this loss function works. But at least at a high level, I hope this made sense. And then we went through inference, where we pass an image through YOLO to get this 7 cross 7 cross 30 tensor, which is 98 bounding boxes with classifications and confidence. We perform NMS, and then we get this cute little corgi and is recognized as a dog. And that's all that we have for today. Thank you all so much for watching. All the resources that I mentioned in this video, including some videos to like the RCNN family of architectures for object detection, like RCNN, the fast RCNN, the faster RCNN, all of those would be in the description below, along with the original papers, the link to the slides, as well as the architecture block diagram that we discussed too. So that's all that we have for today. Thank you all so much for watching, and I will see you in the next one. Bye-bye.